This is the journal track paper. It was published in JAIR 2 years ago, well, a year and a half ago. And so what is hot in classical planning these days? Probably not that. But definitely heuristic search, okay? And if you look at the foundational parts that contributed to these advances, and there are quite a few of them, we identified two. One is monotonic relaxation, and I assume that after 2 days of ICAPS, you already know what it is. Lots of approximations of optimal solutions for monotonic planning problems have evolved into effective heuristic functions, both admissible and inadmissible. The second part is causal graph structure of the problem, especially when it is taken from the finite domain representation of the planning task. And again, it contributed to a lot of practical advancements, mostly around abstraction heuristics, for pattern database selection, merge and string abstractions, fork decomposition, et cetera, et cetera. And recently there is a work that explores the mixture of the two, which is the red-black planning project in which Jorg, Mike, and I worked for 2 years. So if you look at finite domain representation versus monotonic finite domain representation problems, in terms of syntax, they are completely identical. There's no difference. You have a bunch of state variables, actions with preconditions and effects, a cost function if you are not happy with uniform costs. But there's no difference at the level of syntax. The difference comes at the level of the semantics, with the most important difference is that while in FDR action changes value of state variables, in monotonic FDR action adds values to state variables, switching from, well, moving from value switching to value accumulating semantics. And when we looked at our understanding of complexity of planning for FDR and MFDR respectively, so for non-optimal planning, planning for FDR is p-space complete, and for MFDR it's easy. Simple forward chaining procedure solves it in polynomial time. When you look at optimal planning, well, it's not really p-space complete, it's because these complexity classes are defined for decision problems, but you'll forgive me for that. You can solve FDR optimal planning in p-space. And for MFDR, the problem is not polynomial time any longer, it is NP-complete. In fact, it's actually quite a nasty NP-complete problem in terms of our ability to approximate. Now, never scared us a lot. We investigated over the years tractable fragments of FDR and identified quite a few. And in fact, some of them were really helpful in devising heuristic functions. Again, both inadmissible and admissible. So this complexity study actually helped from time to time in practice. And for MFDR, well, nobody worked on that, so we don't know. And this is exactly the point from which we started, advanced a bit, and we'll see where we got. So the basic questions we asked were two. Given syntactic identity between FDR and MFDR, first question is, what are the cases where optimal FDR is hard while optimal MFDR is easy? And you would expect to have such fragments, right? But also the other way around. It might be the case that for some fragments, syntactically defined fragments, structurally defined fragments, optimal FDR is easy while optimal MFDR is hard. Now, who knows? And in terms of parameters, I mean, you can look at all kinds of parameters here. We use two types of parameters. One is the structure of the causal graph. And by structure, I mean all different types of structural parameters, tree widths, connectivity, strong connectivity, node in, out degrees, et cetera, et cetera. And dynamics of single variables that, in particular, exhibited by domain transition graphs. But also, again, the size of the domain per se may play a role here. So just briefly, causal graph is a graph induced by FDR, MFDR tasks. Vertices are just variables, and there is an arc from variable u to variable v if some action touches both variables with touching at least one of the, with touching v in its effect. Okay? Another notion that, I mean, really, I hope you know this notion, otherwise I will spend a lot of time on that, is a tree width of graphs. So tree width is defined for undirected graphs, so we will be talking about tree width of the causal graph. Truly, we will be talking about tree width of the undirected graph induced by the causal graph. And roughly speaking, it's kind of a measure of cliquishness, measure of closeness of the graph to the tree. And it is defined by the kind of node width of minimal with respect to that tree decomposition of the graph. And here's an example of what tree decomposition of the graph looks like. And here, this tree decomposition has the width of 2, which is size minus 1. Now, why this parameter is interesting? Because in optimization, in discrete optimization, many hard problems are known to be solvable in time exponential only in the tree width of the induced graphical structure. This one another graphical structure. And in planning, in 2010, Ronan and I showed that non-optimal planning for FDR can be solved in time exponential only in that tree width of the causal graph and some another parameter which can be quite nasty. Not only it can be nasty, it is not known ahead of time. You cannot induce it from the structure of the problem. Basically, it's the maximal number of times, well, it's an effort required on a single variable to solve the problem. It will show up again later on. So here is the first question we started. So how this table will evolve. On the left, you have the properties of the definition of the fragment, okay? In terms of causal graph structure and some possible additional conditions. They may refer to the structure of the causal graph or to something else. And here the question is, okay, it's polynomial or not. Again, we ask questions about optimal planning. And the basic fragment is, suppose that you have only a fixed number of state variables. Well, trivially, FDR is polynomial time because you can simply compute the whole state space and solve it exhaustively. And the answer for MFDR is no. And I mean, at the beginning, it's a bit confusing, but then when you think about it, it's not really surprising because when you move from FDR to MFDR, you lose all the mutual exclusion relationship between the values of the variables. And it's enough just to take two variables, one to be a parent of the other. Solving this problem optimally becomes hard. So for example, that's background when you use fast downward that gives you this representation of FDR, and then you switch to FF or whatever heuristic that ignores deletes, know that you are losing a lot of information. And by a lot, I mean switching from easy to hard. And I will have to run. Next, we looked at graphs that has fixed tree width. And planning is hard for these problems, even if domain of each variable is fixed. I mean, it is hard even for chain-structured causal graph. I mean, you cannot find a simpler causal graph. And it was shown by Gimenez and Johnson in steps that if the domain is of size 5 or higher, it's an NP-hard problem. And turns out that for monotonic problem, it's okay. So take any MFDR problem with causal graph being of fixed tree width, as long as the domain of the variables is fixed, you can solve it in polynomial time, and the technique we're using there for the proof is based on compiling problems to constraint optimization. Resembling the combination Ronan and I were using in 2010, but different because here you cannot bound the number of time a variable is affected by a fixed number. So if you will be using that algorithm from 2010, you will get something parametric in the exponent. So immediate corollary is that if you have a strips problem with causal graph of fixed tree width, then you can solve H plus in polynomial time. Okay, so now suppose that we want to get rid of this requirement of fixed domain size, because in most problems we work on, there are at least few variables that have unbounded parametric domains. But then you have to bring another set of assumptions. Suppose that the causal graph not only has a fixed tree width, but it's also directed as cyclic, or its strongly connected components are of fixed size. It doesn't matter. Oh, and on top of that, the in-degree of the variables in the causal graph are fixed. You don't have a lot of dependencies for every variable. And again, since the problem for FDR is hard already for chains, we change nothing, it's DAG, and integer bounded by 1. The problem is still hard for FDR. And it is easy for MFDR if an additional property holds, which has a scary name of unfoldability. But basically, in English, it says the true domain transition graphs in monotonic representation are small. So this number of subsets, for example, of values for each variable that you can reach from your initial state is not too large. It doesn't explode exponentially. And it can happen under different conditions. Again, the compilation is to constraint optimization over trees, but the compilation is different. And the key property here that I believe will be exploited in heuristic generation as well over the years is that unlike in FDR, in MFDR, a cyclic structure of causal graph implies serializability of the problem. And it doesn't hold in FDR. So you can solve your roots, then move to kids of the roots, and then to grandkids, whatever. Now, if you want to get rid of that as well, and stay only with DAG, you will have to require a bit more than M unfoldability. And here there are two tricks. First, if n degree is not fixed, you can fix it, as long as the tree width is bounded by a constant. And that relies on relatively recent result by Markov and Shi, which is actually a very cryptic paper. But the result is cute. You can take any graph, and it's tree decomposition of width W. And if it is fixed, you can generate it, actually. And then you can compute a transformation G star of G, in which every node has only, at most, in degree of 3, while preserving the tree width by increasing the tree width by at most 1. That's a very strong operator. It is so strong that it's almost impossible to read the paper. What prevailed decomposability is harder, as I have to finish, is harder a bit to explain, but basically it boils down to there are not too many ways of supporting single variable plans, give or take. And that's it. I think that I'm done. And the colored parts here, I think that the more important results in that respect. I think the role of DAG that shows up here and these yes and no's there are the most important things to remember. Thank you. Sorry for... Actually, I'm 3 seconds behind this guy. So I give you a proof of the main result.